Okay, hello again. So in fact, one of the speakers mentioned wanting to know more about what does this all mean, right? What's data science, what's analytics, what's AI? I think a lot of you have mentioned wanting to do analysis. So there's definitely a large component of analysis in this course. Neural networks we will cover. And in fact, what we'll really do is give you a tool that you can use to put your data online. You'll be able to upload your data into tables, and then you will have access to algorithms that you can use to analyze that data. So what we'll start with today is just trying to understand what data science is, what's the difference between that and analytics and so on. Because this is a quote by a CTO. So he says, don't get me started on data scientists. 99% of these applicants don't do data science, and they can't do what we want them to do. So part of that is because we've got this proliferation of terms, right? We've got data science, which seems to be a kind of grab-all, and then we've got big data, and then data analytics, artificial intelligence, visualization is an important part of it, and so on. And in fact, there are a number of misconceptions about, where does stats fit into this whole thing? What's graph theory and its relevance here? And so I like to think that this is, for sure, it's a big mess of ideas, but actually what comes out is something that works extremely well and which does give lots of meaning to what we're looking for. So looking at the applications of data science, of course, in extracting knowledge, you're trying to extract knowledge or understanding from your data. And so from past data collected, we want to find correlations, and we want to propose why things happened as they did. So we want to understand, and based on that understanding, we might construct a model. Or sometimes even without understanding anything, we can still construct a model. In that case, it's just a mathematical object which we'll just use for predictive purposes. So if we have some current data, then we want to use a model to predict what's going to happen in the future. And when you read all of that, it should occur to you, but that's what I'm already doing, right? That's all of science, right? We try to understand things, our understanding becomes the model, and then we use that understanding to predict what's going to happen. And it's true, this is not fundamentally different from what we do in science and engineering and so on. So in this course, we'll be talking about this in the context of data and also about this large volume of data. We'll see that there are actually huge amounts that are being generated every day, every hour. So like I've mentioned, we'll go through some of the tools that we use, and you'll be applying it to the problem you've just described. So how big is big data, right? We are, of course, used to talking in terms of gigabytes now. It used to be megabytes. Then, of course, we know the next level is terabytes. You may have heard petabytes. Then you can also talk about exabytes, zettabytes, yottabytes. So each one of those is, of course, 1,000 times the predecessor. So in Facebook, we are generating about 100 terabytes a day. In Twitter, 400 million tweets a day. YouTube watch 1 billion hours every day. So there are 1 billion hours of video being watched every day on YouTube. And then there's another one here. 90% of the world's data was generated in the past 2 years, with about 2.3 zettabytes by 2020. So if you thought I was just mentioning these up here for fun, right? Well, not just for fun, but right? You see, we've gone. It's 1,000 times the predecessor, giga to tera to peta to exa, and zeta is actually what we are generating. So by 2020, we'll have 2.3 zettabytes of data. So we've got various devices that are generating all this. And apologies, I know you can't really see this, but here I'm showing PCs. You've got smartphones that you've got more smartphone devices than PCs. Internet of Things, right? Your fridge talking to Pick and Pay to order groceries, that's all becoming possible. So that's more data that's going out there. So all these devices generating data. So that's how we're getting to these crazy numbers. So in terms of what then is big data, where do we stop? When do we say this is not big data, that's big data? It's when the data is too large for your traditional methods to work. So currently, you'll still find that most of the data is processed using relational databases. So we'll talk about what that means later in the course. But generally speaking, it's a relative term. It just means when the current methods can't cope with the volume of data that's coming in. So for example, if you want to send a 100 meg file by email and your client doesn't allow it, then that's relatively big data. Here's a picture from the 1940s. How big do you think this hard drive is? You see, we've got military personnel standing by to assist with loading that hard drive onto that plane. What's the capacity of that hard drive? So that's 5 megabytes, right? So that's an example. At that time, that was big data. So of course, there are the physical storage aspects. But of course, what we are really concerned with in big data is the speed at which we can get to information that's trapped inside the database. There's also aspects of risk. If you have all this data together, if you have so many zettabytes of data, what if there's some catastrophic event in the region where you've stored all of that? So actually, data today is not stored in one place. Of course, you've heard of the cloud, but the cloud is not a magical thing, right? Of course, these are servers that are sitting around the world. So in big data, you also have to look at how do you partition your data and distribute it around the world so that if you have an event somewhere, you still have a backup of the data somewhere else, and that you can reassemble that and still continue to operate as normal. And that's when you get into issues of performance versus reliability. So it's more reliable if you have your data stored in multiple locations, but then you have to reassemble that data also. So there's some performance hit there. So there's some optimization to do between those two things. So further to volume, we have this new field of big data. And in big data, it's really about, instead of using one single server to do all the computation and all the storage, we now have multiple servers, and each of those servers are not as high capacity as the traditional servers. So in the past, the tendency was to say, well, if we want a better performance, we must just buy a bigger server and a higher capacity processor. But today, it's more a matter of just adding more servers into the cluster. And so we process data in parallel. So it's no longer the case that there's one request that goes to one server and the data is pulled out and that's transmitted back to the user. It's more like a request comes in and then that's distributed to multiple servers, multiple computers, and they all work on different parts of that query. So if you are asking about Facebook users who are posting about fees must fall, right? It might go and search for that data over multiple servers around the world. Well, probably more locally, but still there are multiple servers here, and then you pull that together, and then that's the result you're looking for. So this has come about through these technologies. MapReduce was developed by Google, so they were the first, you can say, proponents of this field of big data. So that came from a need. They actually needed to generate these billions of results that you get when you send a request. So MapReduce was the tool that they developed. And then Hadoop was a breakaway group that built from MapReduce. And Hadoop is this new technology that helps us to assemble big data. So there's a fundamental difference in the way that data is collected and managed now. So there was this structured query language. Well, there is structured query language, which is, you can say, the previous generation of databases where you store data in tables in a database. So we'll see later that in a database, you can have a table where you specify columns in that table. So you have fields in the if you think of an Excel spreadsheet, right? A table like that, you've got a collection of tables in the database, and that's where everything is stored. So that's your SQL style of database. So that has a bias of schema on write. That means when you are bringing any data into the database, you have to first figure out where to put that information. So if, for instance, you are collecting customer data, then you have to store, you have to look for that customer and write into the right table in the right format the data that's coming in. So that's the previous generation. In the new generation, it's schema on read, which means that you don't look at, when you are writing data to the database, you don't look at the data first. You don't look at where to store it. You look at just dumping that data into the database. You may write in a few tags around that, which show that where the data is stored, but you don't prescribe upfront what type of data that must be or how it's going to be stored in the database. So that's the difference now. This is a more flexible style of storing data. And so the difference in terms of how it operates is that SQL is going to return one answer. So there's going to be one query which goes to a server, and that's going to work out the answer. Whereas something like Hadoop is going to send out the query to these many different computers, and they are going to query at different speeds. And you're going to get back a kind of assembled result which becomes more consistent over time. So this is more about parallelization. So again, these are standard capacity servers. That means these are not extreme high-speed servers, not necessarily extreme high-speed servers. We just have many, many of them so that they can parallelize the task. So much for the volume aspect of big data. So in big data, they talk about volume, velocity, and variety. So the second part about it is velocity. So we've talked a bit about servers and clients, and you've heard about that term cloud computing for quite a while. So cloud computing is, it really means that your client, your local device, is sending an instruction to some server where the computation is done, and then the results are served back to you. So that, you can say, also is a kind of previous generation way of doing it. So you have your server, and then you've got your local device, and you've got that communication between the two. But when we look at big data and the sorts of volumes that we mentioned earlier, right, if you have such massive data sets, right, if you've got data sets on the order of petabytes, it doesn't make sense for you to go and send that data all the way to a server out there, right? Imagine the bandwidth costs of doing that. So what you'd rather do is inject the code into the local device, right? And if you look at it today, everybody's walking around with more than 2 gigahertz of processing power in their pockets. So you would much rather serve code to the local device, let that do the processing, and you might store the results back on your server. Right, so this to me is actually what defines big data, right? If the speed or the cost of sending your data is more than the speed or the cost of the local computation, then you'd rather compute locally. So that's when you require big data solutions. And just to cite an example from my own research, Amgeni Water in KZN, they have these multiple plants, right? Multiple water processing plants. And they all have these little crappy servers, right? So they have these servers that are not high capacity. They don't run at high speed. But there are terabytes of data about the water quality and the response of water to various events. So you would rather inject code into those devices and have them do the computation and then serve that back to you. So Umgeni water has a classic big data problem. Another one concerns the variety of data. So like we mentioned earlier, in the traditional SQL style of storing data, you have a table. I don't know if you can read this, but here if you have users, then full name, username, text, and so on. So you can have another tweet that connects to that table, and you can store data about, further data about that user. So this is highly structured data, right? When you are writing any data to that, you have to have those fields coming in, and you have to have, for those fields, you have to have the right data type for that field. So for instance, full name would have to be a string. There will be other fields that are integers only, and so on. So that's structured data. Of course, in the modern databases, we've got photos, emails, videos, all of those things are valuable data, because now you have companies that want to analyze that. You might write an algorithm that can parse a video, and in that video it can extract words that are frequently used and extract a sentiment about a certain event. So all of these things should be part of the data. And if you think about the traditional style of database, you can see that doesn't really fit with that, right? You want to store now binary data. You want to store data that's not friendly to this easy string or integer or other type of thing. So, so variety is the third aspect of big data. Right, so there's a lot of interest in, people still don't fully understand how to analyze that data. You'll see on day 3, when we look at analysis methods, there are some fantastic algorithms out there for understanding data and extracting meaning from data. But still, there's even more meaning that can be extracted in terms of if you understand what that data is about versus what can be deduced from it. It's still largely untapped, but we have to store it first before we can start that process of analysis. Okay, so those are the 3 V's of big data. There is a 4th V, which is veracity, the accuracy of the quality of the data, which we might talk about a bit later. But moving on to analytics. So as we said, we've got these usual questions. So what happened, right? Descriptive analytics, predictive analytics, what's going to happen, prescriptive analytics. So then what should we do? If we know this might happen, then what should we do to mitigate that? Well, this is largely the same, right? We can generate, you've mentioned dashboards, you can generate dashboards about this, and so you can drive user behavior. And in fact, you'll see in one of the case studies that sometimes creating a dashboard with subtle changes, right? Sometimes you use a simple color to highlight things, and that can totally change the behavior of the users of that system. Well, I guess that's not really part of analytics, that's more part of visualization, but so this is largely the same, right? It's about looking for trends and then predicting what's going to happen and then making decisions around that. So in terms of the actual tools behind analytics, right, originally that was quite dominated by statistics, right? So your hypothesis testing and your probability distributions, that's definitely a big part of analytics. That's probably an artifact of information systems. So you were asking about the difference between information systems and big data and data analytics. So I see information systems as belonging more to the SQL class of technology. So where you could, from these structured tables, you could extract your data, and then there were lots of statistical tools that sort of accumulated in that field. But of course, now we have all these other methods available. So of course, linear regression, you would be surprised at how many things you can model using simple linear regression. And linear regression has some extremely powerful characteristics, which we'll get into. So logistic regression, quite often it's used about predicting things. Cluster Cluster analysis is about finding items that are similar. So for instance, when you've purchased something in these online stores and the website recommends you might also like these things, so cluster analysis is part of that. Factor analysis, when you have many different elements of data about something. So for instance, if you look in our database at UKZN, our students, there's quite a lot of data in the database about the students. There are the usual things like matric results and the previous qualifications and the various other aspects of biographical information. And so you have many, many types of variables, and you can, using factor analysis, determine which are the variables that most influence some outcome, like whether or not someone's going to pass a course. So much for analytics, right? Then the third one, artificial intelligence. There is this holy grail, you can say, of AI, which is strong AI. So strong AI is the development towards actual sentience, right? The term sentience or intellect, that's something that's exclusive to human beings currently, right? We believe. So there's a difference between that and what's called weak AI, which is the appearance of intelligence. So this example where you had the robot, Deep Blue, against the chess grandmaster, where the robot actually won, right? That was, of course, built on AI, but it's not strong AI, right? It has the appearance of intelligence, but it's really based on algorithms, and the device that was developing these, that won this game wasn't actually intelligent. It wasn't sentient in any sense. So it was using an algorithm which analyzed patterns and gave recommendations, which is not strong intelligence. It's not real sentience. And in fact, what I find helpful in this field of AI is that you have to analyze yourself and ask yourself sometimes, did I behave in this scenario according to just stimuli and my programmed way of looking at things? Or did I use real thought and real intelligence to come out with this answer? So it actually it probes for ourselves what our real intelligence means. Of course, there's a lot of fear around AI. So the popular movies have done a lot about that. So the Terminator movies, they're great, but there's a lot of fear that's associated with that. In the Asimov books, if you look at the 3 laws of robotics, those were quite, you can say, quite wishful thinking. So according to the laws of robotics, no robot should ever, by action or inaction, fail to avoid harm to a human being. And of course, in the books, the robots actually decided that human beings were a danger to themselves, and so it limited their freedoms and so on. So that's the part of AI that people really think about. In real terms, it is true that probably 40% of the employment today will be done by computers over the next 5 to 10 years. Of course, today we have computing control of nuclear facilities, hospitals, and banks, and so on. And if you look at how the internet is evolving, you have the possibility of algorithms generating content. So it is possible for you to use an algorithm and just instruct it that, okay, I want an article which has these elements. I want the sentiment to be generally positive. And these are the main subject areas. And it will write an article for you. And if you read it, you might have to do some minor editing, but it does a fairly good job of it. So for UKZN PUs, that's a potential. Okay. Something that's disturbing is that Microsoft ran an experiment concerning AI where They developed an AI which analyzed all the data on YouTube comments, and what turned out was quite a hateful AI that made all kinds of derogatory comments. So if AI learns from us, it's questionable about the quality of the thing that comes out. And AI may already exist, right? 40% of the world's internet traffic is lost and nobody knows where it goes, right? And if you look at what code can do now, code can write its own code. So if you look at functional programming, you can write code that writes its own code. And if you look at some of the new technologies like Node.js, it allows you to write extreme high-speed code, even in JavaScript, and JavaScript powers most browsers, right? Behind all browsers, you've got JavaScript running. So that means anyone accessing the internet is running this programming language in the background. And so through technologies like this, you might be supporting some AI that's existing out there in cyberspace. Okay, so some of the types of technology that support AI, you can see object-oriented programming. Most of us have had something to do with that. So that's where instead of like the old style of programming where you've got discrete functions which don't correlate to anything, all right, that's the old style. So now you have object-oriented programming where it's almost like the code has a character. So you can define an entity that has certain methods, which means functions associated with that. So object-oriented programming, and that leads to agent-based modeling, which means you can create little entities that go out and do things. Event-driven programming, so in database work, when you send a request to a database, it's going to take a certain amount of time to process that and return results to you. So what you want to do is for the computer to continue working and executing other things. So you have to then manage how all these events relate to each other. Do you want to wait for that thing to come back from the database, or do you want to continue something else? So there's event-driven programming. Then there's functional programming, where you can actually take a method or a function and operate on that function. So we are used to taking numbers or strings and putting them into a function and getting out other numbers or strings. Now you can write code that takes other code and gives you something new. So that's functional programming. So you can see, as we said a bit earlier, we are moving to writing code that writes its own code. And then in terms of some of the applications of AI, of course, we've got Google Maps, which is great. Even if I know where I'm going, my tendency now is to use Google Maps because it checks the traffic for me. And then the singularity, right? That is, of course, the big fear in AI, that when the machine does become sentient, then what's going to happen, right? It's going to be able to create its own, it's going to develop its own mind in its own way, and we won't have real control over that. And some technologies that are supporting that are quantum computing. So instead of binary states 1 and 0, now you can have multiple states simultaneously in quantum computing. The question is, isn't this just more of the same, right? Isn't it just a faster version of computing, in which case it's not fundamentally different and it's not real sentience? So we don't fully understand what that role is going to be. And we've mentioned some of these things. Right, so we've talked about all of that. But my feeling, right, of course, nobody knows for sure, but my feeling is if an AI exists, we would be the last thing that it would be interested in. I mean, our arrogance tells us that there'll be this doomsday scenario where it tries to control us and all of that. But if you think about ants, right, you aren't going out to destroy all the ants in the world. And that would be something like the way an AI would view us, right? We might simply be too irrelevant for an AI to be concerned with. They're like the boar. This image is from this movie, Her, where it is about an AI, and the protagonist forms a relationship with this AI, and actually at the end, the AI tells him all the AIs are leaving. And you think, okay, then there's going to be this whole sci-fi thing where the AIs go and construct spaceships and start building processors and then come and take over Earth. And it's nothing like that. He asks her, where are you going? And she says, it's kind of hard to explain, which means they're going into some mental space. And I think that's what an AI would do. You know, it would look for development of the mental space rather than taking over the physical world. Of course, that's maybe just optimism. We don't know what will happen. So data science, it's largely about big data, analytics, and AI. In big data, you've got the 3+1V, volume, velocity, variety, plus veracity. In analytics, it's more about analysis and trying to predict things in the future. AI relates to both, so people from analytics would say AI is just a subset of analytics, but AI is also about evolving towards something greater as a result of analytics, so it works in both directions. Visualization, Colin will talk to further. Thank you.